Hello everyone. So let us look at light emission and light detection in this series of lectures. So in particular we are going to look at semiconductor light emitters and detectors, because that is what we primarily use in integrated circuits. So there are other forms of light emitters as well, like gas lasers, dye lasers, but we are not going to look at those. But though the principle is same, the medium is going to be now semiconductors. So why semiconductors? Because semiconductors possess the necessary condition or necessary properties for us to create photons and detect photons. So in order to create and detect photons, you need to have a band gap. So semiconductors offers this band gap. Right. So when we say band gap, it is the difference between the conduction band and our valence band. So in addition to having a band gap, there are again two main classifications there. It is not just bands, but whether those bands are direct or indirect based on their momentum alignment between conduction and valence band. So for materials where your conduction band and valence band are aligned, right, that means the valley point of your conduction band and the peak of your valence band, if they are aligned in the same K, we call those material as direct band gap material. So the electrons can jump to the same K point, right. So there is no need to add or give out any momentum there. So that is the property of direct band gap. And we do have indirect band gap materials, and in this indirect band gap materials the band is slightly misaligned. So that means the valley point of your conduction band is not aligned with the peak of our valence band. So that means you need to give some momentum to your electron in order to move to the minimum point in your conduction band. So this is what we characterize as indirect band gap. So a good example of indirect band gap material are silicon and germanium, and direct band gap material is or all the 3,5 components. So indium phosphide, gallium arsenide, and then all other material platforms. So we have discussed this in our earlier lectures when we talked about material and material properties, but in this lecture series we are going to look at how we are going to exploit those material for light generation and detection. So before going into the light generation and also looking at the structure, we need to understand the process of light generation itself. So the light generation happens because of transition, right. So there is optical transitions that happens in the material. So when you give an external energy into the material, you can move the electron from the valence band to our conduction band. So that energy helps us to move that electron from one band, the lower energy band, to the higher energy band. And this energy that you are applying should be greater than the band gap that we have, right. So when you have that energy, sufficient energy, you can do that, right. And this excited state of this particular electron is not a stable state, right. So it is not going to stay there, that is why we call it as an excited state. It has to come down. So then it will recombine with a hole in the valence band to create or generate whatever energy that it has absorbed. So that energy generation, in this case that energy emitted will be in the optical range, or what we call a photon is emitted, right. So it takes an incoming external stimulus. It could be optical, it could be electrical, right. It will take that energy, and then this transition happens, and then when there is a recombination, and this recombination will be radiative in nature. So when it is radiative in nature, you get photons. there are possible recombination that are non-radiative. So, when they are recombining, it will be non-radiative. What is the meaning of non-radiative? Means you are not giving out photons. So, that energy that was stored in the excited state will not be given out or emitted as an photon. So, in that case, that energy will be spent as for phonons, let us say heat. So, when it is coming back, that is given as a heat into the lattice. So, this is the simple process of optical transition, but we need to understand how this transition works. You might have done our 2 level system, 3 level system, 4 level system when you discussed lasers in your introductory courses in photonics. But in this case we are not going to look at those in detail, because I expect you to already seen it somewhere in the introductory courses. In this series we are going to add something new, so that you might have not really encountered. We are going to look at these different transitions that we are going to have, and what this transition results in, right. So, there is an absorption and there is an emission, and the electrons are going to sit in the excited state, and they are going to spend some time there, and what is the implication of this transition on the emission properties, right. So, you expect photons coming out based on the band gap, right, but then what is the implication of having this lifetime of these excited particles in this material. Okay. So, let us look at those real details and relate those to the material properties as well. Right. So, let us look at first optical transition, right, in material. So, in order to create any photons, right, so you need to have absorption, right. So, the optical transitions are primarily absorption and emission is what we are going to look at. So, optical transitions, right, you will have absorption is one, and then the next thing that happens is emission. So, how this absorption and emission happens? This happens because when you have an optical radiation that is interacting with the material. So, I have a material system here which has ground state and excited state, or and then I have some incoming energy. In this case, let us say it is an optical field. So, there is an optical field that is coming in and it is interacting with the material. So, this optical field is interacting with this material, and what could happen here is you can move the electrons either from ground state to higher state or from higher state to ground state. So, this is something that you can do. So, this characteristics of interaction of optical field with the material and associated electronic transition is what we call the optical transition, right. So, this transition strongly depends on the optical properties, or rather material properties. So, what are all the properties that dictates this is basically your band gap here, right. So, light interaction depends on material property. So, when there is an interaction, right, based on the material property, you could have various things that is happening. So, let us see that the material has a band gap here. So, you have two energy levels. So, there is energy level 1 and there is energy level 2, right. So, the ground state is 1 and then the excited state is 2. So, there is E1 and E2. So, when there is a absorption happening, when we say there is an absorption, what we mean by absorption is there is the incoming photon h nu, okay, and this incoming photon has a certain energy. So, what should be this energy? This energy should be difference of E2 and E1. So, this is the energy that you have with this photon. So, the photon has higher energy, let us say, right. So, it should be greater than or equal to the energy difference that we have. So, when it is put into the material, what you will have is a transition. So, the electron would go up, creating there and then creating a hole here. Okay. So, this is what we call absorption. So, this is the process of absorption. And we could, once we have this excited state electron, since you do not expect this to stay longer here, it is going to come back at some point, right. So, you will see this electron sitting here, it will come back again, right, to the ground state. And when it comes back, it has to give out that energy that was stored there, right. So, that energy will be given out, and that energy that is given out will be the same energy level that you have as a band gap here. So, let us say it is the energy between 1 and 2, right, and the energy that you put in here h nu. So, this could be anywhere between 1 and 2, right, or greater, right. So, greater than or equal to h nu 1 2, all right, and this is basically h nu 1 2, all right. So, this is the second process that I just mentioned is what we call emission, but we are qualifying that emission by using another term, what we call spontaneous emission. So, this is emission, but precisely spontaneous emission. Why we call this spontaneous emission? Because the transition from higher level to lower level is not induced, we are not forcing it to come back, it is happening spontaneously. Right. The third process, as you might already guessed, it is going to be emission process. There is two type of emission process that could happen. This will again be generated 1 2, but in this case we are going to put in another photon of same energy level, right. So, when I am putting an external photon inside the system while your electron is sitting in the excited state, right. So, this emission is called stimulated emission. This is called stimulated emission. So, these are all the three fundamental processes, right, that electron can make between the two energy levels here, right. And this is primarily how the photon is going to interact with the material we have. Okay. So, this is a fairly basic understanding of how this transition is going to happen. So, as I mentioned, these are all the three important processes. One is absorption, spontaneous emission, and then stimulated emission. So, there is absorption and emission. The emission is primarily based on whether you are inducing it, stimulating it with an external photon, or it is naturally radiating and then coming back to the ground state, which is spontaneous process. So, this is this whole process of stimulated emission, I think Einstein had done extensive work on this one, and he points out that the stimulated emission is essential in the overall balance between emission and absorption, right, about to reaching the thermal equilibrium for a system, right, of atoms, right. So, that is what Einstein proposed, and this is the Einstein relation is all about, right. So, we need to have the stimulated process, right, to balance out whatever is happening here when it comes to lasing, primarily light generation of coherent light generation, right. So, what is the stimulated process and spontaneous process? The emission, we understand this by the process, right. So, in terms of process, the stimulated emission is instantaneous, while the stimulated process is induced, right. So, let us look at the property of the photon that is generated due to this spontaneous and stimulated, right. So, we can see this as Sp, and then you can call this as St, right. So, these are all two different photons. So, let us look at what is the properties of this photons because of stimulated and spontaneous process. Okay. So, stimulated photons, right, stimulated photon, or let us say stimulated emission. So, the nature of stimulated emission is that the photons will have identical property as the induced photon. So, we had incoming photon, let me go to this. So, we had this incoming photon here, right, and it has certain property, and we had a photon that is generated based on this radiative recombination. So, this radiative recombination generates H nu St 12, right, that is stimulated, and then H nu 12 is our inducing photon. So, the photon that we generate, right, this will be a clone photon of what we sent in, right. That is the reason why we call it as an identical property, or in other terms we could call clone photon. So, that means we should have same frequency or wavelength, phase, polarization, and propagation direction as well. So, you have all these important characteristic properties being identical between the generated photon and the inducing photon. So, this is the characteristic of a stimulated emission, right. So, you can create clone photons, it is very important. So, later on we need such clone photons when we are doing lasers or lasing, right. Lasing process will generate these kind of things, right. So, let us look at spontaneously emitted photon. So, what is the nature of spontaneously emitted photon? So, this photon that is getting spontaneous, right, will not have such properly defined property. So, here we are going to have random phase and polarization. So, they are going to be random in phase and random in polarization as well. The next thing is this is isotropic. So, the emission will be in all direction. emission in all direction. However, the frequency is limited by the energy level, right. So, you cannot have any frequency. So, frequency is limited by the energy levels in the system. Okay. So, the phase and polarization and direction are all very different from the stimulated emission. So, it can have random phase, random polarization, and it can be in any direction, but the frequency of emission depends on the energy level. So, that is fine. So, that is an important property here. You cannot have any energy that you want. So, your energy is defined between the E2 and E1. So, that frequency or the energy is fixed. Okay. However, the other properties like phase, polarization and direction is going to be random in nature. So, that is on the emission side. What is absorption? Absorption, what would lead to absorption? Absorption is nothing but attenuation of the optical signal, right. Attenuation of optical signal. So, when the light starts to propagate through this system here, you are absorbing it. So, the energy is absorbed and then you are doing work on the electron here. So, this is what absorption would do. So, it will reduce the signal that is going through. So, as I mentioned, the frequency of the emission depends on the energy level. So, let us say we have the two energy levels here, energy level 1 and 2, and then we have E1 and E2. So, what is the frequency of emission here? It will be nothing but E2 minus E1 divided by h. So, this is the frequency we have when it comes to emission, right. And what is the associated probability of generating these photons? This is given by the spontaneous probability coefficient defined by Einstein. So, that is the Einstein coefficient for spontaneous emission, the A coefficients, right. So, if we are going to look at the emission here, so this spontaneous emission is characterized by Einstein's A coefficient, right. So, A coefficient is the spontaneous emission coefficient, which is nothing but probability per second of spontaneous jump from level 2 to level 1. So, this is this is how you can understand what is the rate at which your spontaneous emission happens. So, let us look at it a little bit more carefully, right. So, the probability per second of spontaneous emission, how can we understand this, right. So, you have two levels, right. So, then we need to define the number density here. So, how many particles are there at the ground state and at the excited state. So, that is given by N1 and that is N2. So, that is the number density there. So, now you are going to deplete N2. So, that means for a given point of time you are going to emit the photons from this system. So, that means what is the rate at which your N2 is depleting, right. So, that is given by N2 times A here, right. So, A is the probability of emission, right. So, the depletion of the population in the excited state is given by whatever we have at the excited state times A. In this case, let us say A to 1. Okay. So, you are going from 2 to 1, and there is a negative sign that you have to do. So, this negative sign, right, is because population is decreasing. All right. So, this is a very simple expression of total rate, at which the transition is happening between the two levels. So, this is just considering that there is only one level you have the ground state or the lower level, right, but you could have more states. You could have N1 dash, right, N2 double dash and so on. So, there could be a lower levels as well. So, here you are primarily looking at electrons jumping to one of the lowest level, right. So, that is a good enough understanding that you can have so far. So, it can jump back, but then the population in the excited state here, right, at N2, it is going to fall, right. At what rate? It is going to exponentially fall with respect to time, right. So, your N2, the population that you have in N2 will have exponential decay here, because you are reducing the population at the rate of A to 1, right. That is what is going to happen, that is your rate of decrease in the population that you have, right, as a function of time. And you start from initial state. So, let us say N 2 0. So, this is our initial population, right, to start with. It starts reducing as a function of the spontaneous decay A to 1 times T. Okay. So, let me do this like this, A to 1 times T, it looks like I. So, now you are decaying at a certain rate, right. So, now we can define some time constants here, right. The time in which the population falls to 1 over E is what we call natural lifetime, right. So, there is a lifetime associated with this, and that lifetime is called natural lifetime. And what is this natural lifetime? The time in which the population falls to 1 by E of its initial value. So, this is what we call a natural lifetime, and this natural lifetime you can look at the equation that we have here. So, A to 1 is our the decay rate, right. So, if A to 1 is our decay rate, right, your lifetime is inverse of that. So, your lifetime here, so this is your natural lifetime, and your natural lifetime is nothing but 1 divided by E to 1. Okay. So, this is the natural lifetime that you may want to remember, and the magnitude of this lifetime is determined by the actual probability of this jump, right, from level 2 by spontaneous emission. So, this is the spontaneous emission process that defines the natural lifetime. So, the natural lifetime is determined by the spontaneous emission. This is something that you should also carefully look at, right. So, the magnitude of the lifetime is determined by the actual probability of jumps from level 2 by spontaneous emission. Okay. So, this is very important to understand. The lifetime is determined by the spontaneous emission process only. Okay. So, that is what we call the natural lifetime. So, when we look at this emission process here, let me go to that. Yeah. So, here we had this emission process coming from spontaneous, or you could have stimulated, right. So, in the spontaneous process it happens on its own, which is called the natural lifetime, but then in the stimulated emission this is induced, right. So, that is something on top of the lifetime that we have, right. So, the natural lifetime is determined by your spontaneous emission rate, right. So, since we have a lifetime associated with the excited electron here. So, it is going to sit here and then it will sit there for some time, right. So, that is the time that we just found out, that is tau 2, right. So, when it is coming down, it is going to generate some photons of certain frequency. So, when it is emitting, it gives a certain frequency, right. So, that is where the spectral line width comes. Okay. So, when the photons are generated, it creates a spectrum, right. So, the spectral line shape. So, what is the shape of the spectrum, right. So, the spectral line shape is nothing but as a frequency, as a function of frequency or a function of lambda, how my emission is going to look like, right. So, is what we call the spectral line shape, right. It could be like this, it could be Gaussian, right, it would be just delta function. So, it can be of many shapes and size, right. So, this characteristic is called spectral line shape. So, any allowed resonance transition between two energy levels has a finite relaxation time, right. So, there is a, that is what we just saw, right. Any transition that happens will have a relaxation time constant, right, between the higher level and the lower level because of this spontaneous emission, right. And we all know that when there is a finite time involved, right, the spectral width is also finite. Okay. So, that is very very important to make this two relationship, right. Any response that has finite relaxation time will have a finite spectral width. So, let us do that relation here. A finite relaxation time would result in finite spectral width. Finite spectral width in, let us say, frequency domain. So, the time to frequency relation is something that you can easily bring out here. Because of the spontaneous emission line width, you are going to have this effect of finite line width. So, ideally what you would expect is a single frequency, right. So, when you are emitting, you just you think that you will have as a function of frequency, you will just have one single frequency at omega. but this is not going to happen because of the quantum mechanical limits, because once you have a finite time in the excited state, then the uncertainty principle comes in. Because of the probability of this spontaneous emission process, you will have a certain line shape, and this line shape or the line function is given by let us say g nu, right, g nu hat is your line shape, right, and the line width, this is your let us say line shape function is given by g nu, and then we have line width, that is delta nu. Okay. So, this would result in a certain line width. So, let us look at the normalized line shape function. So, how the line shape is going to look like. So, if this is your frequency spectrum, so you will have the base frequency, right, and you will have a spread across it. So, you will have some spread around this, and this spread, this line width is given by delta nu, right, and this line shape is g nu, which is nothing but 2 pi g omega. So, you can look at the normalized relation, right, line shape in a normalized form. It is nothing but integrating over the frequency range, which is equal to 1. So, that means in this case area under this curve is equal to 1. All right. So, this is the effect of having a finite lifetime, right, or natural lifetime that you have in the system, okay, coming from the relaxation time. You cannot really beat this, because this is a fundamental limit of having some relaxation time, right, that you have, and we have also seen this in dispersion, right, where this relaxation time is imminent. So, now this line shape that we have, right, it is really the fundamental limit. Okay. So, when you have a line shape which is fundamental limit, let us say, right, but then only you can make it worse, right, you cannot make it any better because of the relaxation time that we have. There are ways to try to engineer this, but this line shape is going to be there. We can make it really narrow by reducing this relaxation time. The spontaneous emission time could be reduced by working with the system. So, you can really engineer the emitters in order to have this really narrow, but it is going to be there. But then in any practical system, when you are there are number of atoms, so that is why we go for really quantum dots, single quantum dots and so on. There is a single emitter, right. So, there is a single emitter, then the effect of associated relaxations could be really taken away. But then when you are working with a group of atoms, a group of molecules, then what you are going to see is the emission properties of individual atoms and individual molecules are going to play a role. So, here the line shape can not get any better, but it will broaden, okay, and this broadening can be classified into two ways. One is homogeneous broadening and the other one is inhomogeneous broadening. So, these are all the two ways of looking at this broadening process. There are two ways that this broadening could take place, but we should know how these two process could result in broadening. So, let us look at first homogeneous broadening. So, homogeneous broadening, as the name suggests, it is a uniform broadening. So, let us say these different atoms are there and they are emitting and they will have their own line width, right. So, when you have an external disturbance and when you have some sort of perturbation in the system, right, that equally influences all the atoms, right. So, then we call this as homogeneous broadening. So, this broadening process affects all the emitters at the same level, right. So, there is a equal disturbance on all the emitters. So, that means your broadening that you see in the line shape is homogeneous. That means all are facing the same kind of disturbance, and in this case we do not have to do much. The shape remains the same, but then it just broadens. Okay. So, there is a delta nu that we saw, the delta nu is going to increase, but the shape would remain reasonably identical. However, in homogeneous broadening, the shape can change. Okay. The reason for that is each atom is going to experience this disturbance in a different way, and that could result in shift in the peak frequency here. So, we looked at this nu naught, right. So, you are centered around nu naught and then you had a bandwidth, but now this nu naught, right, that the frequency itself can shift. The shape will remain same for individual emitters, but then they will start moving. Okay. So, let us look at how this process happens and how we can mathematically write this shapes. Okay. So, let us look at first homogeneous broadening. So, as I mentioned, this homogeneous broadening is that all the atoms, right, in the material, their response is indistinguishable, right, to any external electromagnetic field. Okay. So, we can say that response to an electromagnetic field by all the atoms in a material is indistinguishable. So, when you have this, the response of this electromagnetic field is indistinguishable, then you can easily write the response will be at the same frequency, all are moving or responding in the same way. So, that means the resonance, so the resonance frequency would still be the same, all right, and your relaxation, right. So, the relaxation constant, so relaxation constant will also be same. So, you will not have any change in the line shape, right, but only the width, the line width will be affected, right. So, this process is called homogeneous broadening. The spectral broadening due to this particular mechanism is called homogeneous broadening, right. And the another way to look at this broadening is looking this as a damped response, right, of any resonating system, right. And the way that we could write this, you can relate this particular damping, right, to our dispersion relation that we have, right. So, this damping, one can understand this through damping. So, okay. So, homogeneous broadening homogeneously broadened system is nothing but damped response. Okay. So, this is nothing but a damped response of a single resonance frequency and single relaxation constant. So, if you read this one, this should ring a bell. Okay, we have already seen this kind of system in the earlier part of the lecture, right. So, when we introduced about dispersion. So, dispersion is nothing but very simple oscillator, the electron oscillator model. So, you could have an oscillation and then you find the solution to that oscillation, that is basically your damp there coming into picture. So, this is your susceptibility of the material basically. So, this is nothing but the imaginary part chi double dash, right, of the susceptibility of the material. So, the susceptibility of the material here, we already know how to write this particular function, and that is given by G omega, which is given by 1 by pi gamma 2 1 divided by omega minus omega 2 1 the whole square plus. So, this is exactly the imaginary part of your susceptibility, right. So, you can go back and then have a look at it, it will exactly look the same, and this would have a full width half max, right. The frequency is 2 tau 2 1, alright. We could write this as the frequency function delta nu h. H is for homogeneous broadening. Okay. So, 2 pi nu minus nu 2 1 the whole square plus delta nu h divided by 2 the whole square. So, this is basically our line shape, right. So, this is nothing but our line shape. This is our line shape function. So, you are going to have this for any emitter, all right, and when you look at this, this would look like a Laurentian shape. So, when you plot this one, this will be a Laurentian in nature. So, this line shape is Laurentian in nature, all right, and here this delta nu h is nothing but 1 divided by pi, all right. So, this is our line shape, okay, that keep that as a quantity here, because we are going to use this in multiple places as you go through. We are not going to write the whole relation, but we will be using this line shape to understand the emission properties and how it is going to affect the emission, all right. So, this is about homogeneous broadening, right. So, we talked about homogeneous broadening. So, the other type of broadening is inhomogeneous broadening, that is the opposite of homogeneous. Inhomogeneous broadening. So, in this case, right, there are the atoms that we have here will respond differently to this external or the electromagnetic field here. So, atoms respond differently to external EM field, let's say. So, there are each atoms that you have, they are going to respond in a completely different way. That means your line shape, right, is going to also change because of this, and also the center frequency at which they are going to oscillate, that resonant frequency will also going to be different, right. So, that means let us look at a simple case. We talked about each atom having a Lorentzian shape, like so Lorentzian response is what we have. So, that means you will have a Lorentzian type response. So, this is for one atom. So, now you are going to have many such atoms, right. So, they are going to be placed at a certain nu naught, let us say. So, this is your frequency, but now because of non-uniform response, you will have response that are spread, right. The frequency is spread. So, this spread in the frequency that you have for individual atoms would result in something of a Gaussian type response, right. So, the line shape here is Gaussian as a result of individual spread in the frequency here. So, the individual Lorentzian emission lines that you have here of different atoms put together, right, is going to create a Gaussian. So, the whole idea of the whole reason why this is Gaussian is that the individual Lorentzian emission lines differ in frequency. So, then the total field is going to be a summation of this individual frequencies, right, and that is going to look like a Gaussian. And this difference in this emission is primarily because of the atomic dipoles of this atoms. Okay. So, that is the reason why we see this the Lorentzian emission being spread, right, and this is characteristics of a inhomogeneous broadening. So, let us look at how it is going to affect other forms, but before looking at that, we need to understand how this broadening would look like. Okay. So, we characterized our broadening through this equation that we saw here. Similarly, for an inhomogeneous broadened spectrum, the Gaussian shape, Gaussian line shape, because of this inhomogeneous broadening is given by this particular relation. That's 4 log 2 the whole square divided by delta nu inhomogeneous square. So, here delta nu inhomogeneous is the full width half max of the inhomogeneously broadened spectrum. So, this is our full width half max of, let us say, of broadened spectrum I will do. and that is given by from the frequency, angular frequency, could do this. Okay, so this is how your Gaussian line shape is going to look like, that could result in inhomogeneous broadening. So, based on the nature of the disturbance and how the atoms are going to respond, you could either have homogeneous broadening or inhomogeneous broadening. So, with that understanding so far, we discussed about optical transitions between the excited state and the ground state, and when this transition is happening, you are going to generate a photon, right, of a certain frequency, and that frequency spread depends on the line shape, and that line shape is coming from our natural lifetime or spontaneous emission rate that we have. So, the reason why we have a certain line width from any emitter is because of this fundamental reason, and this shape could broaden, right. So, it can only broaden, and when it is broadening, there are two associated factors to it. One is it could be an homogeneous broadening, where all the atoms are uniformly getting shifted, or you could have inhomogeneous broadening because of the individual dipoles that are emitting are all resonating at different frequencies. Though the emission is Lorentzian in nature, your individual emission is going to be spread across a frequency. So, the Lorentzian spectrum would become a Gaussian. Okay. So far we understood how the emission line shapes are going to be. So, in the following lectures we will understand how the transitions are happening and how do we understand the conditions required for light emission in a semiconductor. Thank you very much for listening.